The engineering in this, a modern disposable diaper, stuns me. It's a triumph of polymer science. A super absorbent polymer soaks up urine, but that's only part of the story. The brilliant engineering lies in the creation of interlinked mechanisms that operate on different timescales to whisk urine from a child's skin and distribute throughout the diaper to the superabsorbent layer, which then traps the urine. 5 layers comprise a typical diaper. The outermost layer is a thin, soft covering. It's there for the parent's comfort. It feels like cloth, but it's made from plastic. The next layer is a barrier sheet. Typically, it's polyethylene, the same stuff used in plastic grocery bags. Near the center of the diaper, it's edged with elastic to create elasticized leg cuffs. The barrier sheet and the leg cuffs, as noted in one of the many patents, help contain explosive, liquefied bowel movements. They also place all the elements of the diaper in the right place on the child. That's all simple. Where the diaper's engineering astonishes me is in its handling of urine. It must hold urine for up to 9 hours or so as the child sleeps. To do this, the diaper uses 3 layers. The top sheet rests on the child's skin. Bonded to it is the acquisition distribution layer, often called the ADL or the surge layer, and then the absorbent core. The top sheet's behavior surprises me. When I gently place a drop of liquid on the top sheet, it beads up. I've been able to get it to stay there 6 hours. I'd expect it to be highly absorbent, to be hydrophilic, but the top sheet, the part touching the child's skin, repels water. It's manufactured from polypropylene and is hydrophobic. While at first counterintuitive, it's central to keeping a child dry. Urine passes through the holes of the top sheet because it strikes the top sheet at over 6 miles per hour. Once through the top sheet, its water repellence prevents the stagnant pool of evacuated urine from flowing back onto the child's skin. As an engineer, I admire the attention to detail of this top sheet. For example, here's one small but essential aspect. In the top sheet, you see spirals. This is called spiral gluing. It's plastic top sheet melted to bond it to the next layer. This replaced formaldehyde-based glues that irritated a child's skin. The spiral uses less glue than if straight lines were used. Once the urine passes through the top sheet, it enters the acquisition distribution layer, the ADL. As I insult the diaper, the liquid passes through the top sheet and enters the ADL, which swells rapidly. No wonder it's often called the surge layer. What you see is the ADL distributing a localized insult throughout the length of the diaper. As the ADL empties, the superabsorbent core swells. Notice that the ADL is now a barrier to any urine returning to the child's skin. To perform these actions, the section of the ADL nearest the child's skin moves large quantities of liquid quickly, while the outer layer transports smaller quantities at a slower rate but moves the liquid much further. It does this by capillary action. Most absorbent materials, like a washcloth, have channels throughout the fabric. By capillary action, the liquid climbs into these channels. The size of these channels determines how much liquid is moved, how fast, and how far. A capillary tube with a large diameter will move a larger quantity of liquid than a capillary with a smaller diameter. So, near the child's skin, the ADL has large channels. This moves a lot of liquid quickly, fast uptake. And then further from the skin, the channels in the layer are made small. This allows it to move liquid at greater distance, although smaller than those near the skin. You would think that something this absorbent would be made like cloth, that is woven. But to weave something would take a long time, and a diaper machine produces 200 to 600 diapers per minute. To make them this fast, diaper companies created the ADL as a non-woven. In a woven fabric, the strands are carefully interlaced together, but in a non-woven, polymer fibers are suspended in air and then deposited on a moving belt where the warmed fibers adhere to each other. Although this seems chaotic, this allows great control over the properties of the layer. To deposit fibers to create large channels at the section near the skin, and then a more dense network of fibers to create diminishing channel size on the ADL further from the skin. As the urine leaves the ADL, it enters the absorbent core, which stores the urine until the diaper is disposed. The core contains mostly superabsorbent polymer. Here I have 5 or 6 grams of that polymer. I'll mix it with 160 or so grams of water. As the polymer absorbs the water, it swells and turns into a gel. The superabsorbent polymer absorbs liquid in a different way than just capillary action as in the ADL. It also traps the liquid. The urine flows through the channel, like in capillary action, but the fiber itself swells and traps the urine. The long polymer chains expand and form a kind of net that traps the water. It's so effective that in many diaper brands, it's mixed with 15% or so cotton, Otherwise, the gel would block the flow of urine to other parts of the absorbent core. I've celebrated the engineering of a disposable diaper here, but many feel it better for the environment to use a cloth diaper. When I became a parent, I looked for a clear answer to this question, but it turns out to be difficult to measure the impact. Each type of diaper impacts the environment in different ways. The raw material and energy used to create a disposable diaper versus the energy used to wash a reusable cloth diaper. To assess the trade-offs, one must use life cycle analysis and consider a diaper's impact across its lifetime. One fact, though, that struck me was this. A carbon footprint of using a disposable diaper for the 2.5 years that a child is in diapers equals driving a typical passenger car about 1,500 to 2,000 miles.